All right, so let's look at exercise 1 from section 2.2. We're given this function that, let me go ahead and expand this. We're given this function that talks about, or that describes the value of an investment account. That's what V of t is, and then t represents the number of years since the start of 2010. So we're first asked, what's the instantaneous rate of the change of this portfolio's value? So that phrase instantaneous rate, hopefully by now you recognize that that is calling for a first derivative. So I need to find v prime of t. So we've got a couple different rules to follow here. First, I want to obey the exponential function rule. So the derivative of 24 times 1.07 to the t. I think I've said this in a prior video, but when you take the derivative of an exponential function, your derivative will always contain that function, and then you multiply it by the natural log of the base. So times natural log of 1.07. And then for 6 sine t, we have to use some trig rules. So what's the derivative of sine of t? That is going to be cosine of t. So here's the derivative. Now I want to evaluate that derivative at a particular value. In this case, that's going to be 2. That's exactly 2 years after my reference time of January 1st, 2010. So v prime of 2, so 24 times 1.07 squared times the natural log of 1.07 plus 6 cosine 2. So we'll get an approximation for that. So 1.07, the natural log of that should be pretty close to 0, and it is. So times 0.07, 2.07 times 24. So this first term is going to give me an approximate value of 1.859. And then 6 cosine 2. So minus 2.497. All told, I get a final amount of negative 0.64. So that's our number. So what does that mean, and what unit should be expressed in? So basically what we found was dv dt. So we found dv dt at a value of t equals 2. What is v expressed in? That is expressed in dollars. And what is t expressed in? That is expressed in years. So at the start of 2012, the value of this account is decreasing at an instantaneous value of 64 cents per year. All right, moving on to part B. Determine the value of v double prime of 2. So a little different now. We're being asked to, here's the thing to find, now you interpret it. Whereas in part A, we were given the interpretation and had to figure out for ourselves what operation we needed to do. So let's just write down again what v prime of t is, because in order to find the second derivative, we need the first. So 24 times 1.07 power of t times the natural log of 1.07 plus 6 cosine t. So that's the first derivative. The second derivative is the first derivative of the first derivative. So again, the exponential function rule, what that is going to yield here is basically another factor of natural log of 1.07. So I'll capture this in brackets and square it. What is the derivative of cosine of t? That'll be the derivative. That'll be negative sine t. So my second term will be minus 6 sine t. Again, I want to evaluate that at t equals 2. So 24 times 1.07 squared times the natural log of 1.07 squared minus 6 times the sine of 2. So let's get another approximation there. So my first term comes out to 0.126. And what is 6 sine of 2? 5.456. So all told, what do I get? Negative 5.33. So that's the numerical result. So now let's talk about what units that's going to be listed in. So we took a second derivative. So now this is going to be, now we can revisit what the first derivative was expressed in. That was in dollars per year. This will be in dollars per year. Per year. So, or times 1 over a year. Or equivalently, negative $5.33 per year squared. So the rate of the change, the instantaneous rate of change of the instantaneous rate of change. So kind of analogous to acceleration, even though we're not talking about like a physical, mechanical movement here. What does this say about this investment portfolio? So note that for part A and part B, we looked at the same time. That's the beginning of 2012. So from part A, we learned that this portfolio is decreasing in value at 64 cents per year. This tells us a little more. So not only is our investment account decreasing in value, but the rate at which the value is decreasing, that's also becoming more significant. So we would expect that, if we go to February 1st, 2010, we would expect the rate of change to be even more negative. So right now we have a function that's decreasing and which is concave down. Right, moving on to part C. So we want to graph this. I recommend doing a technological approach here. So I will show you what I have on Desmos. And let's just look at all the different things that they asked us to compare. So I graph 4 different functions here. One is the graph of V, which is the one that we've been dealing with. The next one is the graph of A, which is basically a component of V, except it doesn't include that trigonometric portion. So let's look at those two things first. So let's actually change the name to, I'll call this V and I'll call this A, which means I need to change these derivatives names. So we look at V and A side by side. I think it's very much not obvious from what we did in part A and part B, but let's do this here. Let's say X equals 2. So we investigated this account at X equals 2. And at that place, we saw that the value of our account was decreasing. So we're just a little bit to the right of that peak. We should have a decrease there. But since we're just to the right of that peak, that decrease is going to get more significant. So it looks like our investment, if we just look at that very narrow point in time, it looks like our investment account is performing badly. But that really is just because of, where this trig function is in its cycle. If we follow this account for 20 years, we see that the amount will only increase and gets even more significant if I look even like that growth gets more and more significant as we look out further in the future. And that can be seen from these derivatives. So let's turn off A sub X for now. What does V prime look like? So if we look at V prime, what does this derivative look like? There are times early on, it really doesn't make sense to look to the left of T equals 0. Let me turn off this vertical line as well. But if we look at this green graph, which is the derivative, we see that for the first 17 years or so, there are times when the value of this account decreases. But if you look out far enough, like anytime beyond like time equals 17 years, you'll see that this account only increases in value. Sometimes those increases diminish, but the increases are always going to be there, which is something I think is not obvious when we look at this just, at a very narrow point in time, very close to time equals 0.